Hi guys, it's time to learn logistic regression. In this section, we will discuss classification problem and the use of logistic regression to find the answer to our problem. We will also learn how to interpret the results of the logistic regression through a confusion matrix. So let's move on and see what is classification problem and how the logistic regression works for such problems. If you remember, while exploring the linear regression, we worked with the problems where we were predicting the continuous or quantitative outputs like the house price, today's stock price, and such examples. In this section, when it comes to the classification problem, we are interested in non-numerical values, a categorical or qualitative output, like whether the stock price is increasing or decreasing. We have answers yes or no. In this section, our focus will be to learn logistic regression as a method for classification. Today, logistic regression model is one of the most widely used binary model in the analysis of categorical data. Some of the examples include win or loss, whether you are winning a lottery or you are losing a lottery, you passed the exam or you failed the exam, dead or alive, the email you are getting is spam or ham, whether you are getting insurance or loan or you're not getting insurance or loan, healthy or sick, the answer is yes or no. The convention for binary classification is to have two classes, 0 and 1. So when it comes to predicting output class like 0 and 1, linear regression is not appropriate in this case. Why not? Let's learn with some common examples. Let's consider a simple example. We have balance along x-axis and the probability of default along y-axis. The orange ticks indicate the 0 and 1 values for no and yes, whereas the blue line is the estimated probabilities or fit to the data using linear regression. We see the line touches below 0 at y-axis, and if we extrapolate the line along x-axis, the predicted probabilities for higher balances would be much higher than 1. This is classification problem, and it looks like the linear regression is not working in this situation. So we need to find out another way for this classification problem. So the logistic regression is answer for such situation. In logistic regression, we use logistic function, often referred as sigmoid function. The process is very simple. What we do, we take our linear regression solution and put it into a sigmoid function to get the logistic fit to our data. If we fit the logistic regression to the same dataset as shown on the left side, notice that for low balances as shown on the right side, we now predict the probability of default as close to but never below 0. Likewise, for high balances, we predict the probability of default close to but never above 1. The logistic function will always produce a S-shaped curve of this form, and so regardless of the value of x, we will obtain a sensible prediction between 0 and 1. And this is what we want in this case. So now from the logistic regression, we have probabilities between 0 and 1. We set a cutoff point, say 0.5 in this case, so that anything below 0.5 is in no class, whereas anything above 0.5 is in yes class. So once we train our logistic regression model on the trained dataset, we deploy it on the test dataset. It's important to evaluate the model's performance so that we know how well the predictions are. In classification problems, confusion matrix is used to evaluate the model's performance. Let's learn what is confusion matrix, which is also known as error matrix. Confusion matrix is often used to describe the performance of a classification model on a set of test data for which the true values are known. Let's try to understand confusion matrix while testing number of persons for some kind of disease. We have a data set with 100 observations. Out of those 100 observations, there are 43 cases where the patient has no disease. On the other hand, 57 cases where the patient has a disease. Our model is predicting 40 cases out of 43 as no, which is correct, and 3 out of 43 as yes, which is not correct. In case of yes, our model is predicting 50 cases out of 57 as yes, which is correct prediction, and 7 cases out of 57, our model is predicting no, where they are yes. This is wrong prediction. So to understand these numbers, we need to define some basic terminology. Let's consider the trues first. The number in green, which is 40, and our model is predicting as no. This is correct, because in reality these 40 cases are no. True positives are the cases for which our model is predicting yes, and in reality they are yes. So this prediction is also correct. Let's now consider the cases for which the predictions from our model are not correct. In blue, we have the false positives. These are the cases for which our model is predicting yes, where they are actually no. These wrong predictions, where our model is predicting yes for actual no's, are type 1 error. In orange, we have the false negatives. These are the cases for which our model is predicting no, however, these are yes in reality. These wrong predictions, where the model is predicting no for actual yes, are type 2 error. Confusion matrix also lead us to define some other important terms in the model evaluation, such as accuracy, misclassification rate, specificity, and precision. Accuracy is actually how often our model predicts correctly, which is equal to the sum of true positive and true negative divided by the total number of observations. Misclassification or error rates defines how often our model predicted wrong, which is equal to false positive plus false negative divided by the total number of observations. Specificity is defined as when it is actually no, how often does the model predicts no. So the true negatives divided by actual number of no's gives us the specificity. For precision, when our model predicts yes, how often the model is correct, which is equal to true positive divided by the predicted yes. If we look at the numbers, we see the accuracy from our model is 0.90. The misclassification or error rate is very low, and precision is 0.94. So it looks like our model is doing very good. So the confusion matrix is very important in the model evaluation. I hope it would be much easier to memorize the confusion matrix and types of error with this comic. A male is predicted as pregnant by the doctor, which is not a true prediction. This type of error is type 1 error or false positive. On the other hand, A doctor is saying to a pregnant woman that she is not pregnant. This is type 2 error or false negative. Excellent job, guys. We are done with the theory lecture for logistic regression. It's time to move on to the Jupyter Notebook and learn by doing. See you in the next lecture where we will create our first logistic regression model.